In this video, we're going to go over two main things. Heating curves are probably going to be review, but we'll go over it just the same. Bond dissociation will probably be something new. We're going to start by looking at Lewis structures. I'm not going to go over how to draw the Lewis structures. I'm just going to draw them, and then you can see what they would look like. So H2 would just look like this, and that line is worth 2 electrons. O2 has a double bond there. H2O CO2 and then C2H6. So the reason we're doing this is because we're going to talk today about bond dissociation, which just means we're going to break apart bonds. So it's important to know what those bonds are. So for example, if we're looking at H2O, and we're going to talk about the bonds that need to be broken, you would have 2 OH bonds. If we're looking at O2, you would have 1 double O bond. And then here, you would have 6 CH bonds and 1 CC bond. All right, so that's what we're going to be talking about to kind of figure out this math here. So here, we're going to use bond dissociation, and you'll see I'll write not delta HF because we're still talking about delta H, but we're trying to learn bond dissociation. So don't use the stuff that you learned from the prior video. It's basically what those questions are saying. So the balanced equation for combustion of ethane is this. Combustion means we have add to O2, and we end up with CO2 and H2O. So then the next thing is to draw a Lewis structure for all the molecules. We already did that up here, so I'll just rewrite them down here. And you might notice that instead of drawing the dots, I drew lines. For lone pairs, that's fine. Either one is fine. All right. So now we're going to take an inventory of the bonds breaking, which we know is an endothermic process because we require energy to break bonds. So the bonds breaking will be the reactants. And then the bonds that are forming are going to be exothermic. So the bonds breaking, we have 1 CC, which if you look up in your little table over here is 348 kilojoules per mole. And then we have 6 CH bonds. That's for ethane. And then we have 7 halves of the OO, which is 495. Okay, so what you do is you figure out how many bonds you have and then multiply it by the coefficient. So here we had 6 CHs, we multiplied by 1. Here we have O2, we multiply by 7 halves. So when we do that, Whoops, I don't know why I put that decimal point there. We got this number. So now we're going to do the bonds forming. The bonds forming are going to release energy. So as you know, when you release energy, that's a negative sign. So I'm going to do the same thing, except when I look up the values over here, I'm going to make them negative. So we have 4 CO bonds because we have 2 in each CO2 molecule. There are 2 CO double bonds, so we're looking right here, CO double bond, and there are 2 in each molecule, but we have a total of 2 of them. So we're going to have a total of 4, and that's going to be 4 times negative 799. And then our OH bonds, we have 2 OH bonds in each molecule of water, and then there's 3 of those molecules. So that's a total of 6. And that's going to be negative 5974 kilojoules. So all you have to do now is add those together. So the delta H of the reaction, which is also delta H of combustion because it's a combustion reaction, is going to be the bonds that you are breaking with a positive value plus the bonds that you are forming. So that's why we have a negative value there. So that comes out to be 1415.5 kilojoules per mole of ethane. Okay? So it's not a hard process once you kind of get the hang of it. So the only tricky thing here is that you need to figure out how many bonds of each type you have in a molecule, and then make sure that you multiply by the coefficient of that as well. So let's do another one. We have H2 here, O2, and then H2O. The bonds breaking, we have 2 HH bonds, so 436 times 2, plus 1 double O bond, 495, and then forming, we're going to have 4, because we have 2 in each molecule, so 4 total. And again, because it's negative because it's being released. So whenever you do forming, you just change your enthalpy to negative. And then when you add those together, you're going to get So at this point, if you feel like you're getting the hang of it, feel free to pause this video and try it on your own and then come back to make sure you did it correctly. So for CH4, that's our structure. O2. And here's our structure for our product. So the bonds that we're going to be breaking, we have 4 CH bonds here in our methane, and we have 2 methanes. So it's going to be 8 times 413. And then our O2, we just have one of them. And that comes out to positive 3799 kilojoules per mole. And then for our forming, we kind of have a lot going on here. So we're going to have 3 CH bonds. But also keep in mind that you have 2 molecules of this. Okay, so 3 CH bonds, but since there's 2 molecules, we'll do 6 CH bonds. And it's negative because they're being formed. And then we'll add that to, we have 1 CO bond. And of course, make sure you multiply by that coefficient. So 2, and then the CO is 663. And then we also have this OH bond. OH is 463, and we're going to multiply that by 2 for the coefficient. Sorry, this should be negative. So when you do this math out, you get this for kilojoules per mole. Add those two together, and your delta H is this. All right, so delta H is the same, like delta H of reaction, but you'll often see different things: dissolving, dissolution, solution, formation. We've seen a whole bunch of them already. Combustion we just saw. So keep that in mind. They're all the same idea. They just have different descriptors. So let's talk a little bit about dissolving. Sodium hydroxide dissolving is exothermic. It gives off energy. Potassium sulfate is endothermic. It absorbs energy. These are both dissolution because we're separating the ions, and there's no way to tell without actually doing the lab. So one thing you might think is, how can it be exothermic at all if it's dissolution? Because we're breaking bonds. So there's a lot more going on. There are 3 separate processes. Even though you're not seeing that in the reaction, let's take a look at this in 2 different diagrams. So we have this crystal structure, and we're going to talk more about the structure of solids later on this year, but we have this crystal structure. This should look familiar. We have positive and negative ions right next to each other, okay? So in order for NaOH, is that what we're talking about? NaOH to dissolve, energy needs to go in to break apart the crystal structure. That's what you would be seeing as the bond breaking. Energy also needs to go in to separate the hydrogen bonding, which is not a bond, it's an IMF or IPF, interparticle force. So it's going to break apart that bonding. However, energy is going to be released as those ions start to go and make connections with those water molecules. Okay, so you'll see here the negative ion is connected to the two positive hydrogens, and then we have positive ions that are connected to the negative oxygens, and all of that stuff. Okay, that's what's releasing the energy. So it's, even though it looks like all we're doing is breaking bonds, when we're dissolving, you have to remember there's water there too. Okay, now the water is not actually in the reaction because it's not going to change, but it's definitely there, and we are definitely making these connections when we dissolve between the positive ions and the negative ions and the water molecules. So that's where the energy out comes from. So intermolecular or interparticle forces that occur during solution formation, so essentially dissolving. Bonds between the solute particles, that's what you're dissolving, is called the lattice energy. That's endo. You need to add energy to do that. Bonds between the solvent molecules, you'll see that the bonds is in quotes because it's not actually bonding, hydrogen bonding. It's just an IPF, which we'll talk about later this year. And then bonds between the solute and solvent particles, which is essentially just attraction. So you'll see bonds is in quotes again. Okay, those are called ion dipole interactions because it is between the ion and the dipole moment of the water molecule. Okay, so that's where the exothermic part comes in. So that's just a little bit about the energy of dissolving, because if it does throw you off a little bit to see that sometimes dissolving is exothermic, that is why. All right, so here is another diagram. I said we would look at it twice. So here's another diagram of that idea, okay? So again, endothermic, endothermic, exothermic. So just like with delta H and the reactions and the bond, whichever one needs more energy, bonds breaking or bonds forming, whatever one needs / gives more energy, that determines the overall delta H. In a reaction, it's the same thing in dissolution, whatever one gives off or needs more energy. All right, so let's take a look at some questions. This is an energy diagram. Sometimes you'll see them written, I wrote down here, as potential energy diagrams, but we tend to think of those curves as PE diagrams more. Don't get thrown off if AP calls it that. But this is a pretty straightforward thing, okay? The overall is delta H is negative 286 kilojoules. From going from H2O gas to H2O liquid, that's going to be 44. So what's this part right here where these elements combine to form the H2O gas? That's all it's asking. All you have to do is take the 286, subtract 44, and you can ignore the signs since they're all negative anyway. And that's going to give you your answer here. So it's going to be 242 kilojoules. So this question we've gone over before. It's just asking which one is delta H. Delta H is the difference between the reactants and the products. So where you start and where you end, okay? So it's not the difference between the bottom of the graph and the top of the graph or the bottom of the graph and the products. So the answer here is going to be number 4. That's the difference between reactants and products. So this question is saying, for the reaction represented by the PE diagram below, the total bond dissociation energy of the products is blank, the bond dissociation energy of the reactants. The bond enthalpy of the products is blank, the bond enthalpy of the reactants. Okay, so that's asking the same thing. So bond dissociation, bond enthalpy. The answer here is that it is greater than The reason for that is that more energy is produced by formation of the products than needed to break up the reactants. Now you might think it's less than, because when you look at the diagram, you see, oh, it has less energy, right? But remember, we're talking about the dissociation, or the bond enthalpy. Bond enthalpy, not reaction enthalpy. So bond enthalpy, the products, basically that's asking which one involves more energy. Does the forming give off more energy, or does the breaking require more energy? So if it's exothermic, which we know this is, that means the forming gave off more energy. The overall reaction gave off energy. If we say the overall reaction gave off energy, that means that the formation involved more energy than the breaking. So it's a little counterintuitive, but if you think about it for a minute, it does make sense. Okay, so this question is a little interesting, but you can figure it out. The heat of formation for liquid benzene is represented below. The HF for gaseous benzene would be greater than, equal, etc. Okay. So for gaseous benzene, you would have this as your reactants, but you would have gas as your product. Okay? So let's see if we can think about this a little bit backwards. So we would want our overall reaction to be this. We know that if we did liquid benzene to gaseous benzene, that's an endothermic process, right? We know that's an endothermic process because in order to go from liquid to gas, you need to add heat. It needs to be absorbed. So we would know that delta H of this would be a positive number. We don't know what that positive number is, but we know it would be a positive number. Okay? If we combine these two with Hess's law, we can cross out the liquids and get our overall formation reaction. Okay? So all I did here for the overall reaction, in case it's not clear, is I wrote a formation reaction. I took the individual elements of benzene and I just made it gas instead of liquid. So if we add those up, we get the overall formation reaction, which means we would just add our delta H's, okay? Now, we don't know what this number is, but that's not what the question's asking. The question is asking, would it be a greater positive value, a smaller positive value? Would it be negative, or can you not figure it out? If you add another positive to something that's already positive, it's going to be a greater positive value. So this is a tricky question that you have to think through, but you have all the knowledge you need to figure this out. When I'm explaining it, it probably makes sense. It's just when you first read it, you were like, I don't know. So that's why we're going to do some extra practice on this kind of stuff. All right. Following thermochemical equation, the delta HF for liquid water would be the opposite. All right, so this is a decomposition reaction. If we reverse it, we get the formation reaction. So that would give us negative 570, because we'll just put this 570 on the other side, okay? However, don't forget that delta H of formations are always for 1 mole. So the delta H of formation is going to need to be divided by that And so it's going to be this one right here. Now, let's talk about which one best represents the formation of liquid water. We know that it's not going to be these two. That's not what PE diagrams look like. They have a bump, okay? So the question is it endothermic or exothermic? This is exothermic. We just said that delta H would be negative 570 divided by 2. So we would say this one because it is exothermic. So this reaction, this question is asking for what would be the formation reaction for solid sodium nitrate. You could probably write that. All right, so sodium nitrate, NaNO3. If you wanted to write the formation reaction of it, you would have Na, N2, and O2. And then you just need to balance that. So the reason that it's going to be the last one and not the one right above it, even though all of those are the same, is because your formation reaction is always going to have 1 mole. So when you balance this, make sure you're keeping it at just 1 mole. So this isn't going to be, you're not going to put a 3 there and a 2 here, because then it wouldn't be 1 mole. So you will just do it this way. This is just a Hess's law question. In order to get this overall reaction, you would reverse this one. So that would be negative B. You would keep this one. So that would be A. You would do this one multiplied by 3. So that's 3C. And then you're going to need to get rid of the 3H2O that you just did, H2O liquid, excuse me. So you're going to also want to multiply this one by 3. So that's going to be 3D. Oh, I don't know why that negative A is confusing. So it will be A minus B plus 3C plus 3D. So now we're going to talk about units for some of these things that we've been learning about, okay? Now, delta H is energy over amount. So you just go through and pick any that say energy over amount. So kilojoules per mole, kilojoules is energy, amount is mole. Joules per gram, calories per milligram. All of those could be appropriate for delta H. For C, it's going to be energy per amount times degree or temperature. So you can, because it could also be Kelvin. So any that fit that. So here, kilojoules per gram times degrees Celsius. Joules per gram Kelvin. Kilojoules per mole times degrees Celsius. And that should be it. right, so now we're going to finish up this video. We're just going to talk about heating curves for a bit. Heating curves you probably saw in your honors chem class. You've definitely seen this. It was in the first video, MC delta T. Okay. So when you're looking at your temperature changes, you're going to use MC delta T. When you're looking at your phase changes, like going from solid to liquid or liquid to solid, that's called fusion. So delta H of fusion. Liquid to gas or gas to liquid is vaporization. Okay, so you will look up what these numbers are, or they'll be given to you. You take that phase change and then multiply it by the amount you have. That delta H phase change. Okay, these are the only two phase changes that we'll really have delta H for. I'm sure you could find other ones, but it's not usually common to do like sublimation or anything like that. Usually just fusion and vaporization. So this is a heating curve. In your heating curve, a cooling curve is just the opposite of this. So in your heating curve, you have solid, liquid, and gas. And then in between them, you have those changes. So this would be melting. And on that plateau there, you have both solid and liquid. And then here, this is boiling or vaporization. And on that curve, you're going to have liquid and gas. And then once it gets all to gas, it starts increasing in temperature. Same thing down here. You have solid increasing in temperature until it hits the melting point. And then it stays at the same temperature while that energy is converted into potential energy. Then the liquid will increase in temperature until it hits the boiling point. And then that is going to be converted to potential energy. And then it will increase in temperature. Okay, so on the diagonals, you have KE increasing. On the plateaus, you have PE increasing. The last things you kind of need to know about this one is that this is the melting point. And then this is the boiling point. I think that line is not straight. There we go. So let's talk a little bit about these types of curves, just so you have some familiarity. The substance is at its normal boiling point at what time? Normal boiling point just means at 1 atmosphere, okay? So you can assume that these graphs are at 1 atmosphere unless you're told otherwise. So this is asking you, where's the boiling point? We just said the boiling point is right here. So that means 6, 7, and 8 are all at the boiling point. 6 is where it hits the boiling point, 7 is about halfway done boiling, 8 it's finishing up boiling. This question says, the substance is at its normal boiling point at what time? Same exact question, very different answer. Because we only have one plateau here, we don't know what that is. We don't know, and plus it's not all of these are for water too. So even if we had temperatures, we wouldn't know. Because it's only one plateau, it could be melting, it could be boiling. There's no way for us to know. So cannot be determined. If you were calculating the total energy gained by this substance during the heating process, you would be using the delta H of fusion at what time? So this is saying, like we just looked at that slide, this is saying that here, here, and here, you would use MC delta T. Okay, remember that MC delta T is used when the temperature is changing. But here and here, you're going to use those delta H of phase changes. So one of them is going to be delta H of fusion and one's going to be delta H of vaporization. So this is asking you, at what times would you be using the fusion one? And the answer is when it's melting. So that's going to be 2, 3, and 4. A cooling graph, I wanted to go over this just real quickly. A cooling graph is the same thing except it is the opposite. It's going to start at the top. It's going to be gas that's cooling until it gets to its boiling point, and it's going to have gas and liquid there. Then the liquid is going to cool until it gets to its freezing point, and then it's going to freeze, or melting point. And then the solid will cool. Okay, so the same deal as what we had before. So this is asking is, okay, if this is water, where's 0 degrees Celsius? We know 0 degrees Celsius for water is the melting point. So this would be 0 degrees Celsius. Where is it freezing? It's freezing on this plateau in between liquid and solid. Where's the PE changing? The PE changes on each plateau whenever the temperature is not changing, and the KE changes whenever the temperature is changing. KE and temperature are linked. Okay, so there's an example of what a cooling curve would look like. Last little bit is something that you actually don't, whoops. We have one more here. In the cooling curve below, liquid is cooling. When is the liquid cooling? Whenever the temperature is going down, it is cooling. So where is the liquid cooling? Between P and Q. Okay, now we wouldn't necessarily know, because this could be gas and this liquid, except it's labeled liquid solid. So we know the liquid is cooling between P and Q. Now you might notice that there's this little weird dip. Okay. That dip is called something supercooling, not on the AP exam, but I figured I would throw it in here in case you see that dip. I don't want it to throw you off. So there are some substances that it will dip a little bit if you don't stir it correctly. And then it will go back up to the freezing point. Okay, so if you see that, it's not a big deal, doesn't throw anything off. You're not going to be expected to draw one that has that, but if you do see it, I just wanted to throw that in here because this one's a little weird and I didn't want it to mess people up.